Hello people, I'm Bharat Acharya. Welcome to a new video. So in today's video we're going to learn an introduction. We're going to get an introduction to ARM7 processor. In Bombay University we learn ARM7 TDMI, that's the version. In whichever university you are in, maybe the version changes, but as long as it's ARM7, most of these points still remain the same. The family of the processor is the same. Now ARM is a microcontroller. It's a 32-bit microcontroller. That's the first thing I want you to know, 32-bit MCQ. Now, if you learned 8051 and then you've come to ARM, like what most people do, this is a big jump for you. First of all, congratulations, you're learning a processor which is of the modern world. 8085, 8086, 8051, they are like 40-year-old processors, but everybody needs to learn them to get an idea and then launch themselves into higher processors. So ARM is a processor of this generation, and being 32-bit, it is 4 times as powerful as 8051, which is just an 8-bit processor. What it simply means is 8051 could do 8-bit operations in one cycle. ARM will do 32-bit, 4 times that in one cycle. To do the same thing, 8051 would have required 4 cycles. So just by this virtue, it is 4 times faster. Plus there are many more things. One by one I'm going to tell you. Now, I'll give you a brief idea about all these features right now, and then each one of them I'll be making a separate video for this. All these videos will be posted on my own website. It's called 𝗕𝗵𝗿𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀 with your email or mobile number, whatever. And then if you want to watch all these videos, you got to subscribe to the channel ARM. Okay, there's a channel by the name ARM, you got to subscribe to that. The subscription rate I've kept is very low, it's 499, 500 rupees, and that's it. For 6 months you can watch all the videos which are already there, plus all the videos which I keep putting on a daily basis as many times as you want to. I'm sure you won't need it for 6 months, I hope not, I'm sure you won't. Anyway, now let's start. So it's a 32-bit microcontroller. Next, it has a 32-bit ALU. These two properties go hand in hand. Obviously, if it's a 32-bit MUSI, it will have a 32-bit ALU. That means again, it can do 32-bit add or 32-bit subtract in one cycle. It has a 32-bit data bus. What does that mean? It can transfer 32-bit data in one cycle. Now here there is a small point to understand. If you've learned 8086, you'll pick up this point instantly. Now let's start with 8086. There's a reason I'm doing that. 8086 was a 16-bit processor. It had a 16-bit data bus, so it wanted to transfer 16-bit data in one cycle. Now 16-bit data is stored in two locations, two consecutive locations. To read them at a time, they cannot be in one chip, because from one chip you can read one location at a time. So we split 8086 addresses into two banks called even bank and odd bank. It's very similar to your book. In your book you have page number 1, then you turn around, page number 2, 3, then go on 4, 5, 6, 7. Now look at this set of pages. These are 2, 4, 6, 8. So these are even addresses. 1, 3, 5, 7, these are odd addresses. So this is your even bank and odd bank. The advantage of printing on both sides is you can read both sides together, so it makes your reading faster. But does that mean you can read any two pages together? No. You can read 2, 3, go on 4, 5, 6, 7, which means as long as it starts from an even address, you can read two pages together. Now 7 and backside is 8. They are also two consecutive pages, but they cannot be read in one cycle because they are one behind the other. Okay, such data is called misaligned data. So just wanted you to understand there is something called aligned and misaligned data. Aligned data means in 8086 you want to read 16-bit number, it should start from an even address. 0, 1 is aligned, 2, 3 is aligned, 1, 2 is misaligned. Now exactly the same principle. ARM is a 32-bit processor. It wants to transfer 32-bit data at a time. 32-bit data will be stored in 4 locations. 4 consecutive locations. To read them from one chip, they should be in 4, so to read them in one cycle, they should be in 4 separate chips. So these are called 4 memory banks. Okay, this is how it looks like. One chip will have location 0, the other chip will have 1, then 2, then 3. These 4 can be read at a time. 4, 5, 6, 7 can be read at a time. 8, 9, AB can be read at a time, so on. Now, 1, 2, 3, 4 are also 4 locations. But as you can see, they are misaligned. These 3 are first location, this is the second location. Misaligned data requires 2 cycles, cannot be read at a time. Similarly 2, 3, 4, 5, similarly 3, 4, 5, 6. The next aligned set comes at 4. 4, 5, 6, 7 can be read at a time. 8, 9, AB can be read at a time. Now, normal processors like 8086 support both aligned data and misaligned data because that is flexibility, store it the way you want to. But in terms of performance, aligned requires 1 cycle, misaligned requires 2 cycles. ARM is a performance-based processor. Okay, the first few characteristics of ARM will make you understand there is a complete paradigm shift. Here, flexibility is not what we want. We don't mind a rigid system, but a system that gives you mind-blowing performance. That's what ARM does. ARM does not allow misaligned data. Everything in ARM has to be stored in an aligned form. So if you want to transfer 32-bit data or store 32-bit data, it should start either from location 0 or from location 4 or from 8 or from C, which means a location which is a multiple of 4. Now any address which is a multiple of 4 has something very peculiar about it. 0 is 0000, I've just written the number in binary. 4 is 0100, 8 is 1000, C is 1100. What you notice is the last 2 bits of address, the LSB of the address will always be 0. Any number which is a multiple of 4, its LSB last 2 bits will always be 0. Now this is the point. You don't have study of banking in ARM. Okay? Nobody studies banking in all processors. Once you learned in 8086, you know what banking is. But this point will keep coming back again and again. Whenever you talk about an address, this point will come back that the last 2 bits of the address are always 00. Now instead of being lost every time, just wanted you to put the effort and understand it once. That is so that the address is a multiple of 4, so that the data is stored in an aligned form, so that you can do the operation in one cycle. So instantly understand, ARM is not here to please everybody. ARM is not a flexible processor, it's rigid. But if you've been my student, you know this. I keep saying this in all the processors I teach. There's always a choice between rigidity and performance, flexibility and performance. As you make systems more flexible, performance takes a hit. The more rigid you make the system, the faster the system gets. So ARM is more towards performance. It's a performance-oriented processor. That's why everybody finishes learning microcontrollers with ARM. This is like the cream of the whole thing. Yes, it will have a lot of rigidity, but will give you tremendous performance. So here the thing I wanted you to know is, since it has a 32-bit data bus, it wants 32-bit data at a time. There will be 4 banks in the memory, and every data will be aligned. So will be stored at a location which is a multiple of 4. So the last 2 bits of the address will always be 00. That's what I wanted you to know. Now let's go ahead. Again, look at the next point. Typical characteristic of a RISC processor. First of all, ARM has a full form. Okay, some people think it's ARM. No. ARM stands for Advanced RISC Machine. Say again, Advanced RISC Machine. RISC itself has a full form. RISC stands for Reduced Instruction Set Computers. Most of the processors that you would have studied so far would be CISC processors. I'll be doing a whole video after this on comparison between RISC and CISC. There are completely 2 different schools of thought in making processors. CISC processors are more flexibility oriented, RISC processors are more performance oriented. So ARM is a true RISC processor. There are a lot of characteristics of a RISC processor, but this is the most outstanding characteristic. If you want to write a distinguish, I can give you 20 points. If you want me to tell you in one line, single-handedly the biggest feature of a RISC processor is
all instructions are of one size.
In ARM, all instructions are of same size. How many bits? 32 bits. Instructions are fetched from the memory through the data bus. Data bus is 32 bits. If every instruction is also 32 bits, this guarantees that every instruction will be fetched exactly in one cycle. So again, high performance. Anyway, these points become more and more clear as you learn ARM in detail. People have a love-hate relationship with ARM. Those who understand it, they love it. Those who don't understand, they hate it, and they always try to avoid it in their subject somehow or the other. Let's not do ARM and somehow try to pass. Understand it. You've not learned microcontrollers to learn only 8051 or 8085 or 8086. Those were age-old processes. It's like learning ABCD but not making words. You learn all that so that you'll understand big processors. So this is the whole idea behind learning this subject. Okay. So anyways, so it's a 32-bit microcontroller. It has 32-bit data bus. It has 32-bit instructions. Every instruction will be fetched in one cycle. All instructions again are stored in an aligned form. I will not repeat this point again and again. Everything in ARM is aligned. Next, it has a 32-bit address bus. Don't get confused. That was data bus. Here I am talking about address bus. Coincidentally, it's the same size, but they have nothing to do with each other. So the address bus is 32 bits. Now, from the size of the address bus, you can figure out size of the memory. If address bus is n bit, the memory is 2 raised to n. What's the idea? If address bus is 1 bit, it will give you 2 addresses, 0 and 1. If it's 2 bit, it will give you 4 addresses, 00, 01, 10, 11. If it's 3 bit, it will give you 8 addresses. Now get the drift. If it's an n bit address bus, you can get 2 raised to n locations. Please tell me, do you understand? So being a 32-bit address bus, it allows you to access 2 raised to 32. 2 raised to 32 is 2 raised to 2 multiplied by 2 raised to 30. 2 raised to 2 is 4. Don't make me break it down so much. 2 raised to 2 is 4. 2 raised to 30 is a giga. That means 4 GB. 4 GB is the size of memory that can be accessed by ARM. Are you clear? In totality, it can access 4 gigabytes of memory. Now, the next point is related. ARM is based on von Neumann model. So there are two models again on which the memory is managed, the processors are made. One is von Neumann. Von Neumann is the person who came up with the whole idea of processors. So it's probably the father of the subject. You could say it like that. Von Neumann, 𝗏𝗏𝗏 and the brains which made all of this possible. Today we enjoy the fruits of their effort. Anyway, so there is another school of thought, Harvard processors, which are based by which was designed by Harvard Institute. Anyway, so von Neumann model says that there is only one memory in which all programs will also be stored and all data will be also stored. Harvard model says there are separate memories for program and data. 𝗕𝗵𝗿𝗀𝗏, if you've learned 𝗕𝗵𝗿𝗏, it's based on Harvard model. It has 64 KB program memory, 64 KB data memory. In ARM, there is one memory of 4 GB. It contains both programs as well as data, a common memory. So von Neumann model means there is a common memory for storing programs and data. So in this 4 GB, there are programs also, there are data also. Some systems have more programs, less data. Some systems have less programs, more data. That changes from model to model depending on where you're using it. But you have a total space of 4 GB. Spend it the way you want to. Anyway, those were very simple points. Now we go a little higher. It has a 3-stage pipeline. I'm sure you heard of pipelining. Now, if you've seen a 2-stage pipeline, you would have seen something like 8086. Pipelining means dividing the process of an instruction into independent sections and overlapping them. A 3-stage pipeline means, see, I'm sure you know this, every instruction is stored in the memory. The first thing you do is fetch an instruction, then decode it to understand what the operation is, and then execute it to perform the operation. So this is how a normal processor works. Fetch, decode, execute. Fetch, decode, execute. Fetch, decode, execute. How does ARM work? Fetch, decode, execute, 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 execute. Tell me, did you understand this? No? No problem. First it will fetch one instruction. While it is decoding that, it will fetch the next. While it is executing the first, it will decode the second and fetch the third. So what will happen? By the time the first instruction has been executed, the second is already decoded and is just ready to be executed. By the time the second will be executed, the third is decoded and ready to be executed. So it is working on 3 instructions at a time, at one time. One is being executed, the next one is being decoded, and the next one is being fetched. So once the first instruction finishes the whole process, fetch, decode, execute, thereafter all you need to do is go on executing instructions. All the time that was being wasted in fetching and decoding instructions has been totally avoided because of the 3-stage pipeline. Now, this is not cutting edge. This is just good. Cutting edge is 20-stage pipeline, Pentium 4 net burst architecture. That is cutting edge. But anyways, this is better than a 2-stage pipeline. So ARM gives you a 3-stage pipeline. But when I will teach you pipelining, when I will be doing the video of it, you will understand a 3-stage pipeline in a RISC processor gives you higher performance than a 6, 7 or probably even a 10-stage pipeline in a CISC processor. In a CISC processor, because of the flexibilities, pipeline takes a big hit. It gets affected. RISC processors, because of their rigid nature, when they say 3-stage pipeline, they actually mean a 3-stage pipeline. It gives you wow performance. In a CISC processor, 6-stage pipeline gives you poor performance than a 3-stage pipeline because of its flexibility. You'll understand these points when I make the video of pipelining. But anyway, it's a 3-stage pipeline. I hope you understood what's the meaning of 3-stage pipeline. Excuse me. Next, another characteristic feature of a RISC processor. RISC processors are heavily based on registers. CISC processors, on the other hand, work most of the times on memory. CISC processors give you very few registers. Like if you studied 8086, it has only 4 general purpose registers: AX, BX, CX, DX. Even if you use them as 8-bit registers, what are you going to achieve? 8 registers, AL, AH, BL, BS. That's nothing. ARM has, look at that number, 37 registers, and mind you, they're all 32-bit registers. That is not a surprise. It's a 32-bit processor, so obviously there'll be 32-bit registers. But there are 37 registers, out of which 16 are available at a time. Okay, all 37 are not used together. 16 are available at a time by the names R0 to R15. Then you may wonder what happens to the other register. They are called banked registers. If you learn 8051, there are 32 registers, 8 are available at a time, and then you can switch the banks. Not the same thing, but on a similar grounds. When the mode changes, I'll be teaching you all that. When the modes change, some of the registers remain the same, some of the registers become different. So that's how in totality there are 37 registers, out of which 16 are available at any given point of time by the names R0 to R15. We'll be doing a whole video on register model. I will show you how 16 at a time totally becomes, because of the 7 modes, totally becomes 37. That's called programmer's model of ARM. Very important question, whichever university you are in. You, in all probability, you will be getting this in the exam. It's a very important question. Anyway, works on load store model. What does that mean? You want to add, you want to subtract, you want to do anything, get the data into a register. Do not work on memory. Get this clear. These few minutes will make you understand ARM properly. 8085 or 8086 or 8051 allow arithmetic logic operations with registers also and memory also. You can write 𝗕𝗵𝗿𝗀, you can write 𝗕𝗵𝗿 _2000. I'm talking about 8086. 8051, add A, R0, add A, @R0. Please tell me you know the difference between the two if you learned 8051. Anyway, so most processors that you've learned so far are CISC processors. CISC processors allow operations with registers also, operations with memory also. So here is flexibility. As I said, CISC is flexibility based. RISC processors say no such nonsense. All operations will be done only on registers. You want to work on some data of the memory, first load it into a register, then do what you want to do on the register, store the result back in the memory. The only operation allowed on memory will be a load and a store. Nothing else. I'll be teaching you the whole instruction set of ARM. In the whole instruction set, the only instructions that work on memory are load and store. Everything else, be it add, be it subtract, be it multiply, be it anything else, and or XOR, whatever, they will be done only on registers, not on memory operands. You would say this is so rigid. Get this clear. It's this rigidness that gives ARM such good performance. In spite of being only a 3-stage pipeline, as I said, it beats a 6-7 stage pipeline in a CISC processor in terms of performance because of such a rigid architecture, and it has made it very successful. All modern mobile phones use ARM processors. I don't need to say anything more. All of them, okay? They use ARM processors. So that gives you an idea how powerful these processors are. Anyway, so it works on load store model. So what does load store model mean? With memory, this is a processor, this is the memory. Inside the processor there are registers. With memory you can only do a load and a store. Get the data into a register, store the result back into the memory. All arithmetic logic operation, all processing will be done inside the processor only on registers. That's being a load store model. It has 7 operating modes. Yes. I'll just list them. Supervisor, user, system, FIQ, IRQ, undefined, abort. I have given them in a logical order. When you switch on, you are in supervisor mode, you get into user mode, start working all the time. 99% of time you spend in user mode. To make a system call, you go to system mode. If you get a normal interrupt, you go to IRQ mode. Fast interrupt, you go to FIQ mode. There are 2 error modes called abort and undefined. I will be teaching you all those modes. An ARM processor, when it is working, from the time it is powered on till the time you switch it off, it can be in one of these 7 modes. Is that clear? I'm just giving you the names. Of course, I'm just giving you an introduction. I'll be doing a whole video on these modes. That is one of the biggest features of ARM. The next point is totally related. There are 7 interrupts, also called exceptions. Exceptions make ARM enter a different mode. There are 7 modes, there are 7 interrupts. But don't think the 7 interrupts make you enter 7 modes. 7 interrupts make you enter 5 modes. User mode and system mode don't need an interrupt to enter. When I teach, you'll know. Just telling you right now, there are 7 interrupts. Like there are 7 modes, there are 7 interrupts in ARM, also called exceptions. So you got reset, undefined, prefetch abort, data abort, software interrupt, IRQ and FIQ. I've just given the names. There are 7 interrupts. Again, I'll be doing a whole video on this topic as well. Both the videos will be very related. These 2 topics go hand in hand. Okay? 2 sides of the same page, to be honest. Now, or same coin. Next, it has 7 addressing modes. Immediate, register, direct, register indirect, register relative, base index, base with scaled index. There are 7 different addressing modes. What do you mean by addressing modes? The manner in which an operand is given an instruction. When you learn these 7 addressing modes, I'll be of course making a video for it. First time when a student sees it, they think, what nonsense is this? What's the point of having so many options? As you learn them and you understand, each one is better than the other. As you learn up to the last one, as you reach, you're like, wow, what is this? How could people come up with such intelligent ideas? So they all have a reason. Never look at a subject and think you're learning things for no reason. Of course there are. We didn't lift a stone and saw this underneath and discovered it. We have invented this. All of this is created by us, engineers. So if they are created by educated people who supposedly are also fairly smart, obviously each of them have a good use behind them. If you want to match up to their IQ, learn to understand the use behind these things. Then you understand how smartly they're being created and what's the advantage. And the more you understand them, the better engineer you get. Tomorrow you're going to create your own things. So at that time, you should also be creating things which are as smart as these or probably even better. Anyway, so there are 7 addressing modes in ARM. And lastly, there are 3 formats, data formats supported in ARM. I said ARM is a 32-bit processor, so it works on 32-bit numbers. But every number doesn't have to be 32-bit. Numbers can be smaller. So ARM works on 8-bit, 16-bit and 32-bit numbers. 8-bit numbers are called byte, 16-bit is called half word and 32-bit is called word. Now students say, sir, everybody calls 8-bit a byte. That I agree. 8-bit is called a byte. School teachers also teach you that. Since school you know this. In some textbooks, 16 bits is called a word. In some textbooks, 32-bit is called a word. So students say, why is it so contradictory? You know, it's not contradictory. You got to understand the language. The word byte is universal. Byte always means 8 bits, no matter what processor you're learning. The word word doesn't have a standard size. Word size is the size of the processor. If you're learning ARM, being a 32-bit processor, the word size is 32 bits. If you're learning 8086, being a 16-bit processor, the word size is 16 bits. That's why you had an instruction called CBW in 8086, convert a byte to a word. That converts an 8-bit number to a 16-bit number. So students call up and they say, sir, last semester in 8086, you told us word is 16-bit, now you're saying word is 32-bit. Because 8086 was a 16-bit processor, so word size was 16 bits. In 8051, I'm sure you know there's a register called PSW, Program Status Word. 8051 is an 8-bit processor. That register is an 8-bit register. So over there, even word size was 8 bits. Here it's a 32-bit processor, so word size is 32 bits. So once again, tell me the 3 operand sizes. 8-bit is called a byte, 16-bit is called a word, 32-bit is called, 16-bit is called a half word, 32-bit is called a word. Okay? So it supports all the 3 kinds of operands. And there are many more features. I've just listed a few. It's a 5-mark question. These are more than enough to write. I think there are 12, 13 on the board. It supports thumb state, that's why ARM7 TDMI. The reason why I've not put it over here is because maybe you're not learning TDMI, maybe you're learning some other version. Anyway, so TDMI supports thumb state, that T comes for that. It supports long multiply, so that M comes for that. And D and I are because of the debugging, the software and the hardware debugging that it supports. Anyways, I'll be telling you that later. You can write many more features. This is just an introduction. Salient features, they're just your entry point. Now, a few things which I want you to pick up from here is, it's a 32-bit processor. Works on 32-bit numbers, 16 and 8 also are supported. Most importantly, it is rigid. Everything has to be aligned. Okay, no misaligned nonsense supported over here. The only operations allowed on memory are load and store. Everything else will happen on a register. It's a 3-stage pipeline. It has 7 operating modes, 7 interrupts, 7 addressing modes. Those are just points. But the main point was that it is a 32-bit processor and works on 32-bit numbers in aligned form. Everything is in ARM is aligned. So every operation requires only one cycle. Okay, it's a 3-stage pipeline. Fetch, decode, execute are the 3 stages. Supports one Newman model, which means there's one common memory containing both programs and data. Okay, now we'll be learning much more of ARM in the upcoming videos. We've been shooting non-stop day and night. So hopefully these videos should be up within all of ARM should be up within a span of 2 days. That's what I'm trying to do. Let's see. See ya.